Good mornings everyone. In the series of lectures on operating system, today we will start with the evolution of operating system, that is how the operating system started over there. Now, once we say evolution, we can say initially there was need for a hardware upgrade, whereby the moment hardware gets upgraded, once we wanted to make use of that particular hardware, we require some sort of operating system through which those sort of upgrades can be used, or there can be some new type of hardware which may be coming up. Let us say the processor changes, the memory changes. So, all these are nothing but some new type of hardware which are coming up there, or there may be some new devices which may be coming up, like today I may be having some sort of handheld devices. Maybe tomorrow, in case the voice held devices comes over there, then in that particular case what we have to have is, we have to go for the upgradation of our operating system. Or in case I would like to provide some sort of a new services to the user. Let us say today I am providing only a command line interface to my operating system, then that is one sort of a services which are there. Now, tomorrow if I shift to a GUI, that is I shift to graphical user interface, in that case what will happen is, I may be having to add some new features into my operating system. Now, initially we started with a system where there were no operating system at all. What used to happen was, everything has to be done by the programmer. Now, whether it is a loading of program into the system, whether it is a compiling of the program, whether it is a loading of the compiler, every process has to be done by the user only. Now, they used to have some sort of a display lights, toggle switches, or some sort of a input device or printer, through which one would be interfacing all sort of things. Now, IBM 1620 used to be the one system, that is very long earlier days machines, where there never used to be any operating system, every process has to be done by the users there. What used to happen in that particular scenario was, user, let us say user is there, the moment there is a source program, he will be loading this particular source program into the memory. That is, whatever is a program which is there, that gets loaded into the memory at this particular stage. Now, once it has been loaded into the memory, now we have to compile it. Now, what is the programmer or the application developer doing? He is loading this particular compiler there. Now, once he has compiled this, again he gets a list of errors and the compiled things. Now, once he gets the compiled version of the program, then whatever subroutines are to be loaded, again he loads those sort of a subroutines onto the system there. Now, whatever are the linking modules which are to be linked there, again he will be loading those sort of things. So, like this I do not require any operating system at this particular stages, but whatever is to be done I will be doing myself. Let us say I have to load the source program into the memory, I will be loading, I will be deciding in which location I will be loading this sort of a program there. Now, the moment I had to load the compiler, I will be deciding, okay, in this sort of a location my compiler has to be loaded there. So, all the decisions in this particular scenario, where there is no operating system as it is, are with the programmers or with the operators. So, this used to be the scenario initially, once we have got a very big systems, of course, with the very little memory and very with little processing power which used to be there. So, that is why we say it used to be no operating system, and their machines run from a console with the display, lights, toggle switches and the input device and the printers there. Now, what sort of a setup we have to have? We have to load the compiler, we have to load the source program, we have to save the compiled program and loading and linking, meaning thereby everything which what has to be done by the user himself. Now, then came the concept of a batch system. What is a batch system? What we do is, let me say I have got 10 programs in case of a Fortran, 5 programs in case of a Pascal, 2 programs in case of a C language. What will I like to do? Now, in case of a system whereby every time I have to load the compiler, every time I have to run it, in case I do it in the earlier fashion, what will happen in that particular case? My program as such will be loaded. Let us say I am starting with the Fortran program, I will loading the Fortran compiler, compiling one of the programs and then going to the C program, loading the C compiler, loading the Pascal program, loading the compiler over there. So, like this every time I have to compile one program, I will be loading this sort of a program, I will loading this particular compiler every time. So, this is what used to be the earlier system. Now, what came out to be there was a simple batch system, whereby what I do is I combine all the jobs which are related with the particular area. Let us say in case I have got all my Pascal program, 10 Pascal program, I will be loading them once, load the compiler once and compile all the 10 program at one go only. So, what we used to have was, we used to have monitors through which we would be controlling the sequence of the events. What sort of events are happening, we will be controlling with this, and we are trying to batch of the similar type together. And the moment your program is over, there is some sort of a instruction there through which I will get to know, okay, my program is over at this particular stage. So, that is being done by this particular program branches back to the monitor when finished. So, this used to be the concept once we used to have this sort of a simple batch systems. Now, there used to be a job control language. What is a job control language? Through which I can control what is the beginning instruction, what is the end instruction for this particular programming. And my job control language that used to provide instruction to the monitor. And what sort of instruction are there? Okay, what is the compiler I had to use, what data to use, also this sort of a things I had to inform to my computer, okay, this is the way I am going to deal this. So, this is all this particular aspect are being handled with the help of this job control language there. Now, in case of a simple batch system, what used to be the memory layout over there, okay, we used to have operating system in the top memory, and in case of a user program and everything, that has to be there in the user program area there. Now, my user area program can contain number of programs at the same stage there. Now, what sort of hardware feature I will be looking over there? Now, maybe I am looking for a memory protection. Okay, what is the memory which I allocated to one program, so that the same memory I will not be allocating to the other program. This is what we call as a memory protection, that is, do not allow the memory area containing the monitor to be altered. Okay, whatever are the memory areas which has been allocated by the monitor, I will not be altering that, and I must be having some sort of a system through which I can protect that my system is getting monopolized by the one sort of a job there. So, this is what we have to see once we have to think of this sort of a systems. Maybe timer is one of the methods through which we used to decide, okay, this much is the time which I will be assigning to this particular job. Now, there may be some concept of a privileged instructions, that is, certain machine level instruction can only be executed by the monitor. So, what came out to be there was, okay, there may be some monitor instruction, there may be some user instructions. The instruction which can be given by the monitor cannot be given by the users there. So, those sort of instruction we used to call was the privileged instructions. The privilege concept of privileges, okay, every monitor has got its own privilege, user has got its own privilege. I cannot go into the privileges which are being given to the users and monitor, or I cannot jump to the privileges given by the users there. And then came the concept of interrupts. Maybe earlier system they never used to have this sort of a concept of interrupt. The moment one program start executing, nobody can stop them till the time that particular job is complete. So, those sort of things we used to call was the interrupts. Now, then we have to think about some sort of a method through memory protection, that is user program executes in a user mode, that is, and monitor execute in a system mode. So, this used to be, there is two types of executions there. That is what we have got as, we have got a user mode we used to have a user mode memory or the system mode. That is what used to be there was, okay, in case of user mode memory, this is, let us say, this is the my memory which is there. Let us say this is my user mode memories, let us say this are my processes which are there. I have to think about some sort of protections over here, that is P1 should not be interfering with the memory of a P2, P2 should not be interfering with the memory of P3, and P3 should not be interfering with the memory of the P4. And same way I have got a system mode, that is whatever has been allocated to the system, I must protect. Let us say this is my system memory, I must protect this particular memory from rest of the memories over there. So, this used to be the concept of the memory protection. So, in case of a user program executes in a user mode, certain instruction may not be executed at all, and monitor executes in a system mode. So, these are the two modes which came up there, and there may be a kernel mode, that is another thing which was added, through which all sort of a privileged instructions are executed or protected memory may be accessed in that particular case. Now, another thing came up there was, okay, my CPU may be fast, but my IO processors, IO devices may be slow. So, what happens, let us say for example, let us say we have to read one record from the file, it may take 15 unit of a time, and once I were to execute 100 instruction, I may be taking only 1 unit of a time, or once I have to write one record to the file, I may, let me say, I may be taking 15 unit of a time. So, if you look at the difference between these two timings, okay, reading a file, writing into the file, they are the slow processes which are there, whereas once I have to execute the instruction, that may be a very fast instruction there. So, what happens into this particular case is, the moment my job which I have been assigned to the system has gone to the IO processor, maybe at that particular time my CPU is not doing anything as far as my system is concerned. That is, okay, my system percentage CPU utilization time reduces to 3.2% in case I have got this sort of a process there. So, in case that is what the problem used to be there with the uniprogramming, that is, in case I am executing only one job at one particular time, then the processor must wait for IA instruction to complete before proceeding. That is, once it has to proceed for the next execution of a next instruction, it must wait for the IO instructions to be completed. That is, in case, let us say as I was giving the previous example, okay, it may be taking 1 unit of a time to execute 100 instructions, and it may take 15 unit of a time to just read one record from the file. So, that means the time of 1500 instruction will be wasted in case I go for the uniprocessor system over there. So, this is what happens. Let us say I got a program A that is running, and there is a some sort of a wait there. My processor will keep on waiting till that time that IO is over. Again it will get a slot to run, again it will wait, again it will get a slot to run, again it will be waiting over there. So, like this is the how my processor will be executing my job in this particular scenarios there. So, what is happening in this particular case? I am running my program. Running of a program means I am utilizing my CPU at this particular stage, but I am running at this particular stage, but rest of the time I am just waiting over there. So, this is what is happening. Okay, in this particular time I am just waiting for the system, my IOs to be over. Once I say IOs to be over, reading the file, writing to the file or printing the file. So, at this particular time I am just waiting, and then again I get a small slot where I am executing my program, and again I am waiting for the IOs to be complete over there. So, this is thus used to be the scenario in case I have to execute my program in case of a uniprogramming mode over there. Now, then since there is a problem in case of a uni mode, that there is a lot of wastage of a time over there. So, what we have to do is we have to reduce this particular waiting time there. So, how can I reduce this waiting time? Maybe I can put up more number of jobs there. That is, the moment one job has gone for the IO, I should be able to put another job over there through which my system can be operational. That is, in case of a multi-programmed system, what we do is we put several jobs are kept in main memory at the same time, and the CPU is multiplexed amongst them. That is, first characteristics is I will be putting in case of my memory, in case of a multi-program system, I will be having one portion for the operating system, rest of the portion I put it for my jobs, let us say J1, J2, J3 or J4 or J5, maybe, or you can use P1, P2, P3, P4, 5. So, this is what we have got jobs over there. So, if I look at my CPU, let us say this is my CPU, this will be multiplexing between these few jobs over there. Maybe it takes this particular J1 job here, executes it, and the moment my execution is over, then it is goes into the terminated state. And let us say the moment this has got into the terminated state, my next job will be loaded there, and this particular job goes from here. Now, let us say this job, while it is getting processed, there is a need for it to read some sort of information from hard disk, or it has to print something onto the printer. So, what will happen? Let us say it goes to the printer. The moment this job has gone into the printer, now CPU time will not be wasted in this particular case, but there will be another job which will be getting into the CPU at this particular stage. So, this is what we call as the multiplexing of the jobs. The moment one job is taken away from the CPU, another job comes into the CPU at the same time there. So, this way I will be saving lot of my CPU times there. So, this is what we say, several jobs are kept into the main memory at the same time, and they are multiplexed over there. So, this is how my system look like. Okay, I have got operating system and I have got a number of jobs there. So, as we said, okay, this is the linear memory which we have got. Maybe I have got a memory location from 0 to 512 K. So, this is what I have got the memory, and these are the some of the jobs which has gone into this particular system there. So, this is what the moment one job needs to wait for I/O, the processor can switch to the other job. So, this is the basic philosophy based on which multi-programming systems are designed. That is, one job is over, it puts the another job, but one job goes for the I/O, it again puts to the other job there. So, this is how my system will look like. Let us say there are two programs, program A, program B. Now, program A is running, rest, and the moment there is certain I/O, there is some sort of wait which will be there, and again it will run, and again it will wait. Now, program B, let us say at initially it is waiting, then it runs, then it waits, then it runs, then it waits over there. Now, once we combine them, what do we mean by saying we are combining them? We are having the multi-programming there, that is these two jobs are there into the memory. In combined approach, I will be saving this sort of a wait time for the execution purposes. So, this is what we call as the program A, program B, and the combined execution which will be there. Now, if you observe in case of a combined thing, we are able to save lot of our time. We are able to save lot of idle time of the CPU in this particular scenario over there. So, this is how my CPU utilization is there. If I look at CPU, memory or disk or terminal or a printer, in case of a uniprogramming and in case of a multiprogramming, there is a lot of utilization of the CPU in this particular case. There is a lot of memory utilization, lot of disk utilization, and all this are nothing but some sort of a parameters based on which I can decide about the performance of the system, maybe CPU, memory, disk, terminals, printers, or the job history, the way it has been executed. Now, if you look at the job history in case of a uniprogramming and multiprogramming, maybe in case of a uniprogramming, I may be taking more time as compared to the multiprogramming there. Now, what happens in case of a multiprogramming is, okay, let us say you imagine there are 5 jobs which we have put into the system. Let us say I have got this particular memory there, and this is the CPU which is there. Now, what happens is, let us say I have got this P1 job, P2 job, P3 job and P4 job. Let us say my P1 job is a CPU intensive job. What do you mean by CPU intensive is, okay, there is no IO instructions there, it is all CPU instructions which are there in this particular. Same is true with the P2, same is true with the P3, and let us say P4 is a IO intensive job. What is the IO intensive? Okay, it may be taking lot of IOs once it is to process this sort of a job there. Now, what will happen in this particular scenario is, okay, the moment P1 jobs get into the, let us say it requires 10 minutes, 10 unit of a time, this requires 20, this requires 15, and since this P4 is a job where there are not lot of IOs there, let us say it requires only 0.1 unit of a time before it goes to the CPU, before it goes to the IOs there. Now, the moment it execute this P1, since this is a CPU bound job, it will utilize all its 10 unit of a time before it shift to the next job. And same way, the moment this is my next job, the moment it, since again this is a CPU bound job, it will again complete its 20 units of time before it shift to the next job there. Now, and then comes the turn of the P4. So, what you will observe in this sort of scenario is, okay, we are having this P1, P2, P3, P4 as a 4 jobs. Now, P1 will take 10 units of a time, it will take 20, it will take 15. So, that means before P1 gets his 1 second of a time, it will be, we have to wait for all these sort of minutes over there. Maybe it will have to wait for 45 unit of time. So, this is what we call, okay, it has to wait for a very long time in case of a multiprogramming. Maybe I just require only 1.1 unit of a time, but I had to wait for all these minutes before I get my this 0.1 unit of a time here. So, these are some of the problems which arises in case we go by this sort of a approach over there. Now, next is we try to see in case I can allocate some amount of a time once all these jobs are getting executed there. So, this sort of a approach we have got is a time sharing approach. What is the time sharing? We use multiprogramming to handle multiple interactive jobs. Now, what we do is we process the time is shared among multiple users, and multiple users simultaneously access the system through the terminals. So, that is what happens is each of the system gives a time slice to each of the job which has been assigned to this. Let us say, as I give you the example, we have got a P1, P2, P3, P4 as the jobs which requires to be executed. What I do is, instead of giving all the 10 unit of a time at the same time or 15 unit of time at the same time, what I do is I just allocate to each job one, let us say, some time slice, we say it is a small time slice is there which I allocate to each of the job in a sequence. So, this is how it look like. P1, P2 jobs are there. I will be allocating some amount of a time, let us say E naught or I naught is some amount of a time which I am giving for the execution purposes. The moment its time is over, in spite of the fact the job may not be complete, still I will be allocating this sort of a time to the next system there, next process which is there, that is allocated the time. Like this I keep on allocating the time, and maybe if you observe, the job which is requiring only 1.1 unit of a time will not be have to wait for such a long time before getting its turn for the execution purposes. So, that is what we say is system that allows multiple users to run concurrently, and the system switches from one user to the other. So, this can be the scenario. Once my jobs are executing, it can be job 1, job 2, job 3, they are the ones which are executing in some sort of a sequence there. Now, for the historical purposes, the first time sharing system was developed at MIT, and later on it was incorporated in most of the system which has come up. Now, what is the algorithm for time sharing system? We select the first program from the scheduling list, that is whatever program has been scheduled, we just take the first program and allow it to execute for a fixed amount of a time. The moment that particular time is over, that is we just load the value of the time slice into the interval timer and start execution of the program on the CPU. Now, if the program initiate IOs, let us say I have allocated some time slice to this particular process, but in between it just initiates some sort of a IO there. Now, what we do is we will not wait for it to complete its IO, but we will send it to the other scheduler. We call the scheduler and ask for the another job over there, or my job can be finished if it is a IO is there, or there is some sort of a timer interrupt. What is the timer interrupt? The moment my time slice is over, I have to take out another job from my job scheduler and allow it for the execution purposes. So, there are two scenarios in which my job can be taken out from the CPU. One is it goes for the IO, that is, let us say it has been given 1 unit of a time, and once it completes half unit of a time, it needs the CPU, it needs the IOs. The moment it needs the IO, that job is taken out from the CPU and another job is put it on the system. Or another scenario can be, my job is executing, but there is the time slice which has been allocated to this particular job is over. What I do is, I take out this particular job from the system and preempt the program and load the another program into the system there. And what I do with the program which has been taken out from the CPU, I add it to the end of the scheduling list. So, whatever is my scheduling list, let us say there are 4 programs already there, this will become the 5th program there. So, that is how my this sort of a thing will look like. Okay, processor 1, process 2 and process 3 will be executing in this particular stage. Now, at some stage it will be blocked and in some state it will be the running state there. Now, then another type of a system we have got, we call them as a parallel system. Now, up to now, whatever system we have gone through, we have just assumed that one processor is there and it will executing only one process. Now, what happens? In case I have got a number of processors there, let us say there are 3 processors. What I do is, I break my job. Let us say what happens is, let us say there are 3 CPUs. Let us say this is CPU 1, this is CPU 2 and this is CPU 3. Now, what does my parallel system says? In case I have got one job over there, let us say this is my job which was there in the memory. Now, in the earlier system which we were talking about, we were assuming that there is only one job which goes to one of the CPUs, but in this particular case what we do is, we just break this particular job into smaller parts. Let us say this is a J1 for this particular part and this is J2 and this is J3. Mind it, it is job A which is there, which has been broken into 3 components. So, what I do is, I just allocate this part to this part to this and this part to this. So, this sort of a things whereby we are doing some of the jobs parallel, we call them as a parallel system. So, for in case I have to have this sort of a system, I have to think of a parallel operating systems there. Mind it, in this sort of a scenario, what we require is some sort of a different languages through which I can develop the program which can be broken into smaller components. So, this is what we have got parallel systems. Okay, these are the multiprocessor systems. One of the characteristics is, this sort of a system they have got more than one CPU who works in a very close association. Okay, there is some sort of a communication which keeps on going on between them. Let us say one system has finished, other system has not finished, it will wait for another system to finish up the job before it goes to the another system. Now, in this particular case we have got a tightly coupled system. Now, my processor and the clock, they may be shared by the system there, and communication it takes through the shared memory. Now, that is a tightly coupled system. We have got a loosely coupled system where there can be different systems through which we are going for this sort of work there. So, how does my program gets executed in this case? Maybe I have got a main program, I have got a child processes. Now, every process it has got a child processes there. Now, I may be executing this child processes while my main program is getting executed over there. Now, it executes first child process, then it goes to the other child process. Simultaneously, there are other 2 child processes which are there, which are getting executed there. Now, then next type of a system which we have got is, we have got a distributed systems. What are the distributed systems? Okay, there may be number of systems which we would have connected by some sort of a communication way. It can be some sort of a network of a computer which can be there. Now, what happens in a distributed system? My system can process its work on his system, or it can process in somebody's else system there. So, what will happen in this particular case is, okay, I may be having a local LAN, my database is lying at one system, my processes are lying at one system and they are executing in between. Let us say you can think about the railway system and the airline reservation system which we got. Those are some of the example of a distributed system. Maybe sitting here, I am accessing the database which is lying at some other site, or database which is lying on my own site there. So, this is what we say, we can be distributed computation among several physical processor which are there. Now, there can be a loosely coupled system, just like we have network system. We give the example of a network system as a loosely coupled system. Okay, each processor has got its own processor, its memory, and they communicate with one another through some sort of a communication lines, such as high speed buses or the telephone lines. And its a basic requirement is, it requires some sort of a networking infrastructure through which it can communicate, and it can communicate either through local area network or through the wide area networks. One is, there can be all sort of a system which are connected, we call them as a loosely coupled system. Every one system has got its own clock, on system and on processes there, and they work in a asynchronous mode. Whereas, I can have a tightly coupled system, whereby I have got a one system and a central pool of a memory there, which is being used by all the systems. Now, then we next type of a system we got is the real time systems. By real time system we mean it may be processing some external processes there, that is, there is my application program, it is based on some sort of a interrupts, some sort of a responsive from the external systems, and that there is some sort of a maximum time determined by the external systems there. Let us say you imagine you got a system of the oil refinery. Now, what happens is, let us say there is some sort of a crude oil which is coming out of the pipeline, and I may be having two diversions over there. You can imagine this sort of a scenario. Okay, it gives the good oil and this is some sort of a bad oil. Now, this may be based on some sort of a viscosities which I may be checking through my system there. Now, this can be an example of a real time systems, where is what is happening is there is crude oil coming. Now, I had to decide at this particular some sort of a sensors are there. The function of the sensor is it senses whether the oil which is coming is of good quality or of the bad quality. Now, based my system, it sends the sensor sends this information, and based on this information some decision is taking whether this oil has to go through this pipe or it has go through this pipe there. So, this is can be one example of a real time systems. Now, there is a very great time constraints over there, time constraint in the sense that the time it takes to process this particular data and close this particular process here is very rigid. I can't say that within this there can be some flexibility over there. These are rigid timings which are there. So, within this particular rigid time it has to respond back. So, this is one example of a real time system, or it is used for the power transmission and other purposes. Idea is there is some sort of a external entity which is there, which is performing some task. Based on the task, some decision has to be taken by there. So, that is why we say it is often used as a control device in a dedicated application, maybe controlling scientific experiments, MIS, industrial control system, and other some of the display systems. Now, one of the characteristics of real time system is it has got a well defined fixed time constraints. Okay, whatever time constraints are there, they are very fixed and they are very well defined over there. Now, we usually say real time system may be either hard or a soft real time. We are not going to details of all these things, but there can be hard real time system or there can be soft real time systems there. Now, then we have got a handheld systems, maybe your PDAs, your cellular telephones, maybe you might have seen the present day telephones which you have got, your mobile telephone, that has got its own operating system there. But that has got challenges there, how do I design this sort of operating system which fits into very small memory, very small processor which may be available to me. So, what I do is, maybe you might have heard of my cell telephone, it has got a Windows on it. That does not mean whole of the Windows will get into my system, but maybe only a part of the Windows which is necessarily required for my cellular telephone may be available to me on this sort of a system there. Now, what are the major issues which are there in case of a handheld system is, it may be having very limited memory which is available to you, or the processor which is available to you may be very slow, or the display screen which is there, it may be very slow. Maybe if you look at your cellular telephone, the screen which is there is very small, but still I have to have all my icons on this particular small screen over there. My processor may be slow, but I have to process the information. My memory may be very less, but still I have to put the required sort of a software into this particular system there. Now, as an example, we usually take Windows architecture. This is the most modular structure for flexibility. In case of a Windows only, I can correlate with the PDAs, I can correlate with the cellular phones, I can have a smaller Windows. I can have a there are operating system through which I can design my own operating system. What I do is, Windows is one of the examples. I take part of this, put it into my operating system, new operating system which I would like to have it for my mobile system, and then I compile and make it as a user defined operating system there. So, this what we say is the application written for other operating systems there. Now, in case of a modern days operating systems, these are some of the features which are there. One is a microkernel architecture, that is, we just assign only a few essential function to the kernel, rest of the things I keep it as a some sort of a library, some sort of utilities there. Maybe that helps to take care of my address space, inter-process communication or the basic scheduling. Maybe my kernel as such takes care of this sort of things there. Or there another concept which is coming very fast is the multi-threading. That is, what we do is we just divide my process into small threads, then can be run concurrently. And what is a thread? It dispatch a unit of a work. Any small, we usually correlate with the processor also, process also. Any small process, we call it as a thread there, and it executes sequentially and is uninterruptible and is interruptible. I can have an interrupt in this case also, and every process can have more than one thread in this particular case. Maybe Java language is the one example through which I can design multi-threaded applications there. Or it can be a symmetric multiprocessing, we call it SMPs. Since there are multiple processes there, this processor can share the same memory and the same IO facilities there. That is, in case I have got a symmetric multiprocessing, I know this process will be following this particular process, this will follow this particular process, they will be executed in a synchronized mode. So, I can have some sort of a memory, some sort of a IO facilities which can be shared amongst themselves only, and all processors can perform the same function in this case of a modern, in case of symmetric multiprocessing. Or it can be distributed operating system, that is, it provides you the illusion of a single main memory space and a single secondary storage is there. Now, what happens in this particular distributed operating systems are, user does not know whether he is working his own system or he is working on somebody else's system. My operating system give me the illusions Okay, everything is available to you on the same system there. So, that sort of a system we call as a distributed operating system, and there are distributed applications which are made on the distributed operating systems, or there are certain object oriented designs. Okay, we have got a object oriented design for the operating system, whereby my operating system is a modular. I keep on adding some sort of a modules into my operating system there. That is, it enables programmers to customize an operating system without disrupting the system integrity. That is what happens is Linux is one of the example of this sort of a scenario, whereby I keep on adding some sort of a modules into the existing system there. We call it as a open systems also, or system where we can keep on adding some sort of a module into the existing systems there. So, this is what we had done today. We had just tried to see how my operating system have evolved over the years. Initially, we started from a stage where there never used to be operating system, and we reached to a system whereby I can design my own operating system. In that particular transition, we came up with a uniprocessor system, we gone through multiprocessing system, we gone through time sharing system, we gone through real time system, we gone through parallel systems there. Now, idea is I cannot think of all this system in isolation. I can't think of a time sharing system without multiprogramming, or I can't think of a multiprocessing system without time sharing and multiprogramming there. So, once we integrate all this operating system into one, so we get a combined complex operating system over there. We thank you.